Get started here. So we're going to skip down a little bit further in the slides today, kind of start at a different point. So I want to make sure we kind of go over some stuff. It'll be a little bit out of order. We'll revisit some of those examples on Monday. Just kind of as a reminder, Monday I will be here recording. Doesn't matter what group you're in. If you want to show up, you can, just based off the responses. There won't be enough people to kind of fill the room. So if you want to show up Monday, no matter what group you're in, you can. I'll be recording here, or you can kind of log onto the Zoom call as well. We'll kind of still be on Zoom. And if you're already starting kind of your traveling, that video will obviously be posted as well when I'm done with recording all classes on Monday. Okay. So we've been talking about regressions, how we interpret things, how we can think about using these coefficients. We'll go through a couple other examples today. Some additional things that we can do. So up to this point, we've kind of only looked at linear relationships, right? So this was the idea. We had this line, and we were trying to get estimates for what A and B were, because what A and B told us was, look, if I want to predict what Y is, right, and kind of think about, even I just want to think about these are predicted Y values. If X is 0, right, it's going to start at whatever my coefficient estimate is for that intercept or that constant, right? If X is 0, 0 times anything is 0. So my predicted Y value at X is equal to 0 is just the intercept. Right? We then said the slope of this line would kind of be this B hat. So, if I plugged in any value for X, I could predict what that Y value should be. Right? If I plug this value in for X into this equation, once I have these coefficient estimates from Excel, I could come up with that predicted Y value. Now the problem is, I'm going to need an eraser, so I'm going to use this chair. So, that's great if the data looks something like that, right? That line kind of best fits that data. The problem is that line doesn't best fit the data. If it looks something like this, I can't draw a line that kind of best fits it. In fact, the line that would best fit it has a curve to it, right? So how can we get an estimate if we have something that looks like it's nonlinear? Okay? If we think a little bit about mathematics, right? If I want to have any kind of curve, what I'm really saying is, yeah, the value of X matters, but also, we'll call this B1, B2. We can add in a squared term, right, to try to kind of get a little bit of curve in that relationship between X and Y, right? We'll then get kind of a coefficient estimate on that squared term, and that now would allow us to kind of know what the intercept is, but plot out kind of that relationship between X and Y if it was nonlinear. Okay? So all we're going to do is kind of include this squared term. Excuse me. So if we think about, I think I have an example here. Current slide. Okay. So we had that kind of standard. Let's think about the length of a bluegill and kind of its age, right? So we're going to try to predict what the length of a bluegill will be. So in case you don't know, that's a fish. And how old it is, right? So it may be that the initial days of a fish, maybe it grows a lot faster in the first year of its life than it does in the last year, right? So it might be that if we're just thinking about what's the effect of being 1 year older, or here 1 day older, right? Well, that's going to be very different depending on where that age is starting out. Am I thinking about a 1 day increase from 0 to 1, or from 5,000 to 5,001, right? If I think about days, it'd be much older fish at that point. Kind of think about humans the same way, right? If I wanted to predict somebody's height based off their age, well, initially 1 unit increases in their age will cause big kind of changes in their predicted height. But once we get to age 30, that effect we kind of know is 0, right? So there's going to be some nonlinear relationship there. Okay. So we could just first start out kind of predicting that naive linear regression that, well, it doesn't matter how old the fish is, every additional day it'll kind of increase in length, right? So we would think that as it gets older, right, that the length of the fish will get larger. And so we're probably thinking beta 1 here, or kind of think about this, sometimes the way I write it is B1, right? Probably positive, right? Probably a positive relationship between age and like the size of a fish, right? So I had some data, sure enough, I ran that regression. Notice age is a pretty good predictor of the length of a fish, right? We're already up to an R squared of 0.73, or we're explaining 73% of the variation in length of a fish just by its age, right? Controlling for no other like environmental factors or anything, not even kind of the gender of the fish, right? Which we know probably will cause different predictions. So I've got this coefficient, and it is highly significant, right? However, we kind of already talked about, right? It might grow quicker in early years of its life as opposed to when it gets older, right? So if we're thinking about what this looks like visually, it's likely that we think about kind of the age of the fish, and we're trying to predict the length. It's likely that initially, being 1 day older, right, causes a huge jump in Y. Being another day older causes a huge jump in Y. But eventually over time, right, it gets to a point where the fish is full grown, it stops growing, right? So we're thinking about we probably have some type of relationship that looks something like this. Okay? So in that case, right, we're thinking about our predictions. Here I'll just keep it, you don't have to think about prediction yet. So go T1 on age and B2 on age squared. We can see that there's a positive relationship. So it's likely that kind of this is positive, right? It's increased, length is increasing as age goes up, but it's increasing at a decreasing rate, right? So if it's increasing at a decreasing rate, we're thinking about B2 there is probably negative, right? As the fish gets older, kind of that relationship starts to kind of level off. Right? So let's look and see if we include that term, what we actually get, right? So let's just include this new variable, which is age squared. And I'll show you how we can do this pretty easily in Excel if we don't have like the age squared variable originally downloaded. So we estimate this equation in Excel, right, just by adding in that age squared term. Right? And I kind of mentioned, if we think about here, here if I've got kind of this kind of down, which is kind of an upside down U, or kind of this concave kind of line here, right? We would have, thinking about that square term being negative. If it's kind of increasing at an increasing rate, we think about it as being positive, right? I talked to this specific example, but this is just kind of more general, right? So, part of this is, I guess, unless we look at a scatter plot of the data, we're probably kind of hard to guess maybe on some examples what that squared term will be. But a lot of the times, like in the kind of age and human height, or the age and length of the fish, we probably could think about kind of visually what that would look like. And then once we draw what we think that relationship would be, depending on which, what the example is, once we draw it out, we can kind of think about, okay, we likely could expect the intercept to be positive or negative here. But we won't actually know, maybe my intuition was wrong. Maybe that's not, maybe what I drew up here on the board, I don't know, maybe that's not it. Maybe a fish grows faster once it's like older. I don't think that's the case, but we can see from the regression output. Okay. So I'll kind of skip through this a little bit because we already talked about that. So let's just look at the output, right? So we look at this, we run this regression, and sure enough, still looks like there's a positive relationship between age and the length of fish. But notice, now if we kind of we think about what's the total effect of being 1 day older on the length of these fish, well, the problem is, if this goes up by 1, this would also go up by 1, right? So now I can't just interpret, this isn't solely the effect of being 1 year, or sorry, not 1 year, 1 day older on the length of a fish. We're gonna have to kind of use both of these coefficients. But before we get to that, before we understand how we can find what we call marginal effects, right, notice that squared term is significant, right? E to the -6 means move this decimal 6 places to the left. This is a very small p-value. We can reject the null. With these squared terms, it's the same as what we were doing before. We start out assuming that they're equal to 0, right? That there's no relationship. So we found here, this is pretty significant. It probably is that this is a better model of predicting the length of a fish. In fact, what's another way we could do that? Well, what's another statistic that tells me kind of how well my regression is doing at predicting the y variable? There was a kind of another statistic that told us how kind of it was a measure of how much of the y variable we were explaining, which was the mentioned on the last regression I showed you. This r squared, right? R squared is telling me what proportion of the variation in my y variable I'm explaining with all of my x variables, okay? Or if we think about, we usually like to talk about things in percents. This is a proportion. I'm explaining 80% of the variation. Before, when I only allowed this to be a linear relationship, right? When I only included just the age variable, kept it linear, I was only explaining 73%, right? So you can think about it as this model or this second regression is a little bit better at predicting kind of what the length of that fish will be if we allow that relationship to not just be linear but nonlinear. Okay? So we have a positive coefficient here on the non-squared term and a negative coefficient on the squared term, which is, you know, our intuition was right? It's going to look something like this, right? Where it's increasing quickly initially, right? So we've got this pause relationship, but it kind of decreases over the age of the fish. Okay? Any questions on this before we keep moving here? Is this making some sense? Kind of taking you back a little bit to like calculus or something like that. Okay. So what's the total effect now? Before, when we had these coefficients, I wanted to use this to be able to say, you know, if I think about, if I think about when I simply had kind of the linear relationship, I could interpret this coefficient as if the fish is one kind of, I think it was day here. I said it was days. Maybe it seems maybe more like this was years. But 1 day older, this was the kind of expected increase in the length of the fish. Right? I'm sure this was measured in kind of something like fairly small, so probably something like, I don't know, millimeters or something like that if we're talking about days. Right? So now that I have this additional squared term that I know is also, like, it's still age, right? If age goes up by 1 unit, both of these variables would change, right? So what's the total effect, right? Well, if I'm thinking about, and this is where, actually I can leave that here. I'm gonna do a little calculus here, but shouldn't be too bad, right? If I just had, well, we'll keep this specific to our example. So we'll do length plus b times age, right? If I want to know the effect of age on length, I would take a derivative. I could think of this as length as a function of age. So if I take a derivative of this function in respect to the x variable, well, if I take a derivative of this function, what am I left with? So think about the derivative of f of age, or kind of think about y here, in respect to age. All I'm left with is b, right? If I take a derivative of this function in respect to age, I'm just left with b. Okay? What if I now have a length as a function of age, but now that function has this additional squared term? So we'll call this b2 times age squared. Well, now the effect of being 1 day older, age going up by 1 unit, if I take a derivative of this function in respect to age, now I've got this, right? So the effect of being 1 day older, this is the total effect. It will still depend on kind of the age of the fish, right? So I'll have different marginal effects, right? The effect of being 1 day older will vary depending on the kind of the starting point age of the fish. Right? But it doesn't matter. I can still come up with kind of what these marginal effects would be. I could just think about this as here we go. I now have this equation, and if you tell me the age of the fish, I could tell you that if it was 1 day older from whatever starting age it was, what the expected increase would be in its length. Right? Because I'll have estimates for beta 1 and beta 2, or kind of as I have up here, B1 and B2, and then I just have to plug in the age of that fish. Okay? So, you know, I want to think about what I could then do is think about how does this effect vary depending on the age of the fish. Just start out on my x-axis. I think about now. I'm looking at different ages of the fish, and I can think about my marginal effect and how that will vary depending on the age. Right? So I start out here. Remember the marginal effect. Nope, I forgot my 2. Right? Depends on the age. So at age 0, the very first day of its life, if I plug 0 in here, the effect would just kind of be wherever B1 is, right? So I forget, I think it was something like 55, maybe. Right? And then as I go from, if I start at being 1 day old, and I go to being 2 days old, so I plug in kind of started at 1, right? Or age 1, I plug this in. Well, now it's what? B1 plus 2 B2, and then I could plug in 2. But I would just kind of go through this process, and I basically would be able to kind of map out this marginal effect. So I'll show you how, in the next example, how we could do that. Now in practice, you don't have to do that, but it just kind of gives you an interesting kind of outlook about what those marginal effects are. So let's think about if we had a slightly different example, and I'll show you this one in Excel. So let's say I'm trying to predict GPA using the SAT score variable, and now I combine this with, I can also still control for a lot of other factors, right? So I can still allow this relationship to be quadratic, right, and not be linear, but I can still control for, you know, other things like whether or not they were student athlete, kind of race, gender identifiers, all these other things we had in that GPA data set, okay? So if I do that, right? When I said what might I expect the sign to be, I mean, we looked at last class, the relationship between SAT scores and GPA was positive. So I'm probably thinking about this is going to be, you know, something where, I don't know, like my initial intuition might be that, you know, going from a 1,000 on the SAT score to an 1,100 might not give me as much predictive power about what someone's freshman year GPA would be. Whereas if I saw someone go from a 1,500 to a 1,600, that's a lot harder to do. That might be a lot more informative. I don't know. That might be my intuition ahead of time. But it doesn't matter what my intuition is because we can go to that GPA data, kind of that initial kind of raw data that we had. Go up here. Now I'm just going to move these around so I can have the results kind of right next to each other. So let's say I didn't have this SAT score variable. So I moved my data over 1. I'm then going to put in here SAT squared. All I do is take this, raise to the second power, right? So I'm just going to create a new column, which is my SAT score squared. I think last class I showed you if we want to do something, maybe it was a couple classes ago. If I want to do this, I can double click here once my mouse turns to this kind of plus sign, double left click, and it fills that entire column of data for every observation. I then go to data, data analysis, go down here to regression. My Y variable is what? College GPA. My X variable, let's just include all of them. All right, so I included every single variable that I have. I selected the labels. I want it on a new worksheet. I hit OK. Oh, what did I do? Did I select over to L? Doesn't like here. B1 through K1. So what is that telling me? It's telling me that I have some missing data. That lin S tells me I have missing data. So this is actually probably good. I'll show you a pretty good way kind of check to see where the issue might be, right? We can use that filter option, but there's also another thing that we can do, which is count blank. So now if I select the range of data that's above this in my data set, so Control Shift, hit the up arrow, go down one, so I'm just looking at the data, not the label, and I hit enter, that will count the number of blanks that I have, right? So if I copy this over, here's the variable that I have a blank in, right? So I'll go up, high school rank, and I say, where's that blank? It's right here, so I'm going to get rid of this for right now, just for the sake of this example. And then go back here, select all, so I can see my data again. So if I gave you, like I think I mentioned this last class, if for some reason I happen to give you a data set for your individual assignment where there was a missing, that's another way of kind of quickly identifying it. All right, now I got to go back down here because when I select my data, I don't want to include that count function that I put in. All right, let's try this again. Data analysis. Select my Y variable. Select my X variables. Control Shift or Command Shift on the Mac down arrow. Have my labels. Now I've got this output, okay? So what I can see here is, okay. So now I've got that, it looks like initially, and this is where we have to think about marginal effects, okay? Now it looks like there's a negative relationship between the SAT score and someone's predicted GPA. But remember, this isn't the only coefficient that matters, right? The marginal effect, right, we had included this coefficient, but also this coefficient as well. And this coefficient, although very small, is positive. And these are small because we're talking about 1 point increases on the GPA or on the SAT score, right? So what I can do, right, and these are both, p-values are small, so they're both, you know, significant. I can reject the null hypothesis that there is a significant relationship between the SAT score and the SAT score squared with my Y variable of GPA. Okay. So we look at this output. We go down here. We'll kind of use these values, right? So this was our coefficient on the SAT score. Here's the coefficient on SAT score squared. So I moved that decimal point 6 places for us, right? So if I'm trying to kind of predict what my GPA is, wait, this is not, hold on, what did I do here? I could come up with different predictions if I had just kind of only included these two and left off all the other kind of control variables, right? I could come up with what this prediction was. Now, notice, I mean, when I have really low kind of SAT scores here, how can I get a predicted negative GPA? Well, this is where sometimes we have to think about the context of our example, right? So why is this negative? Right? Why could I have these negative GPA predictions if I use this? Well, if we think about it, right? If I'm trying to come up with what these marginal effects are, right? It's not very, like I talked before, we could like map these out. Well, at very low SAT scores, right? Like if I put a 0 in here, my coefficient on just the linear term was negative. Well, that's because no one you see as a freshman in college has a 0 SAT score unless, I mean, assuming that we have students that took it, right? I mean, so the very kind of high, you know, lowest SAT scores that we even start seeing, right, would be, so if we think about here, we want to map out the marginal effects. We think about the levels of SAT scores. I mean, even at like a 500, right? I'm thinking about kind of a 1600 point scale here. I think you'd be probably hard pressed to find a lot of like, especially like D1 University, a lot of college students who got a 500 total on kind of their SAT, right? That's pretty low. So, I mean, yes, we can come up with what the marginal effects are for that range, but this doesn't make any sense, right? We're just never going to observe that in the data. Same kind of thing you could do, like, I don't know, like something that kind of depends on age. So if I'm thinking about, I'm trying to predict you know, the number of accidents that somebody's in their lifetime, and kind of, or how many they've been in at that point in their life. Well, I'm not going to see any drivers like below the age of 10, right? So if I can make predictions, if I have that variable of age for if a driver was 10, but I'm never going to observe that in the data. So sometimes you can get some kind of wonky things like that happening where if I really look at this line, the marginal effects are probably going to be positive once we get kind of past these really low SAT score variables that we're probably not even seeing in the data anyway. So we think about this, right? And I'll come back to this here in a second, because I'll grab these, right? I'll get that marginal effect equation, right? Plug in my coefficients, okay? So I want to think about, oh, maybe I don't have it here. Oh, shoot. Was it in the Excel file? Oh, sorry. Just want to exit that. Thought I had. Here it is. I was going to say, I know I had it somewhere. So kind of notice, sure enough, if we use those coefficients and kind of graph out what those marginal effects look like, okay, we can kind of see, yeah, anything past like a total SAT score of 600, the marginal effects are positive, right? So it makes sense, right? Any actual person that we look at will think that as they score higher on the SAT, we would predict that their GPA would be higher, right? And as we get to higher levels, 1 point increases moving from like 1500 to 1501, we're going to predict larger jumps in the predicted GPA than if I see someone go from like a 600 to a 601. Okay? Now, like I said, you don't have to map these out every single time, but it kind of maybe lets us kind of think about them a little bit better. Like I said, we're never going to see somebody with SAT scores kind of in this range in the context of the example that we're talking about. Okay, so I went through some of that kind of quickly. There's some other, little comments in here. But, I've already kind of mentioned these, right? So there's some of these bullet points or things that I've already kind of said out loud, right? It's pretty reasonable that we only see scores past like 500, and, we wouldn't think about anything below 500 even showing up in our data set, okay? And then we kind of talked about, we could use these to get that graph in Excel. I'm not going to ever expect you to do that, so that's why I just kind of showed you the graph and not kind of the process. Okay. All right. Any questions kind of up to this point? Okay with this? All right, so this is should be helpful on the last question of the Excel assignment, which I think I have the due date set as the Friday after Thanksgiving. Right, so the 4th, I think it is, December 4th or December 5th. I forget the exact date. So let's say we think that there's a nonlinear relationship, right? But we are, instead of kind of including this quadratic term, we can do some things that are a little bit different, right? So, our typical beta 1 or B1 interpretation was a 1 unit increase in X would cause a beta 1 predicted change in Y. So it's really treating going from 1 to 2 the same as going from kind of 10 to 11, right? But if we think about, these are 1 unit changes, but what's the percentage change? What's the percentage change if I go from 1 to 2? That's a 100% increase, right? Whereas going from 10 to 11, well, that's only a 10% increase, right? I won it by 1 unit, but that's only 10% of where I was starting. So if we think about maybe we're not as concerned with unit changes, but we're really concerned with like the percent change in a specific variable, we might want to do something like this, okay? So what we're going to do is we're going to take the natural log of both of these variables, okay? If we take the natural log of both these variables, the new interpretation of beta 1 is if x1 goes up by 1%, right, we would expect a beta 1 percentage change in y. So, without kind of walking through all the mathematical proof of why this works, right? Let's just take it for granted that if I take the natural log of both these variables, it now allows me to interpret my coefficient as if x goes up by 1%, I would predict that y goes up by beta 1 or B1%, okay? So these log-log, the coefficient is interpreted a little bit differently, So let's think about an example, right? So maybe I've got height and weight, and I'm going to use the same data set for all these. It may not be that each one of these is appropriate to apply to this specific data set, but it allows us to look at kind of the differences or think about the differences of these models. So if I had a data set with height and weight in it, right? And perhaps I think that, well, if I'm trying to predict, oh, I want to do this way. I think the actual, what did I do here? I think I flipped these around. That doesn't make any sense, right? I'm going to try to predict weight using height. And I think that's what I actually did in the Excel file. Okay? So if I'm trying to predict weight using height, I might think about, maybe 1 inch isn't as, I don't know, good of a measure, because the percent change in your height might affect weight more, right? If I go from 5 foot to 5'1", maybe that's different than going from, I don't know, 7 foot to 7'1" in terms of predicting weight. So I take the natural log of both those variables and then kind of I run my regression, right? So how would this look like in practice? What would this look like in practice? So I'm going to show you these results, but I'll show you with this GPA data set how we could do this in practice, and then we'll just look at the results. Okay? So I'm just going to copy and paste this over here. I'm going to zoom in a little bit. Okay. So all I'm going to do is create 2 new variables, and I can just use this equal sign ln. It'll just take the natural log of GPA for me. Okay. So once again, kind of a nice shortcut. If I double click, left click here, copies it all the way down. I'll then do the natural log or equal sign ln of my SAT score variable, right? Double click on, left click on that little box. Now I've got these 2 variables. Now, when I go to my regression analysis, I've got the new variables I want. It's as simple as, well, now I'm going to use the log of GPA as my y variable, and I'm going to use the log of SAT score as my x variable, right? So once I've created these new kind of columns or variables in my data set, it's as simple as, well, those are now your new x and y variables you want to select for your regression. Okay? So then I would, select, here we go, got labels. Why is it not like this? Did I copy and paste something weird over? Oh, I might have some zeros somewhere in here, and I can't take the I can take the natural log. No, I can't take the natural log of 0, so that's probably why it's mad. But that's how you would do it in practice. That should work. If you do have a variable for your data set that has like negative and a lot of 0 values in it, let me know ahead of time. We can try to figure out something else for you to use, or I can kind of give you a little bit of direction and how you can get a natural log or a log-log regression to run. Right? But if you do that, as long as you don't have kind of like 0 values in that variable, then you should be okay. So maybe if we have time, I'll kind of fix that and show you how we could identify the zeros. So if I run that regression, right, here was kind of the basic one, right, where I didn't take the natural log. So the impact of being 1 inch taller, right, in height predicted that someone was 4.7 pounds heavier. Well, now if I use the log-log specification, if someone is 1% taller, we would predict their weight would go up by 1.7%, right? So that's the kind of difference in interpretation here. Now, if we look at the R-squareds here, what model might I think is a more accurately capturing that relationship between height and weight? Yeah, so we call this the log-log model, and this is the level model, right? We're looking at level changes, unit changes. So here's our level model. Here's our log-log model. Well, if I'm explaining 22% of the variation in y here, but only 20 over here, well, then this is going to be the model that's more accurately capturing the relationship between height and weight. So if I'm trying to make predictions, I might want to use kind of this model to make my predictions based off of, or base my predictions off of this model. Okay. All right. So I kind of already went through what that interpretation of the coefficient would be. 1% taller in height, you would predict 1.7% heavier in weight. So is it, what's another way that we could kind of think about, situations where maybe this matters? A lot of the times if we're looking like income, revenues, populations, units sold, because these things vary in levels so much, anytime you see variables that vary a lot in just the level you could see them, a lot of the times it's probably that percentage changes matter more, right? So what's one type of independent variable that we couldn't use? Well, anytime we have dummy variables, right? We can't take that natural log of 0. And so anytime we have dummy variables, we can't use a log-log model for that variable, right? So we can really only use it for these kind of variables that have non-zero values, or these kind of dummy variables. Right? So an interesting way to think about these log-log models is what's something else in which we might want a percentage change in this would predict this percent change in this other thing. Right? Well, kind of taking you back to 201, maybe some stuff that Professor Nesson would talk about, right? Elasticities, right? Elasticities, we were looking at percentage changes, right? A percentage change in price caused this percentage change in quantity. Well, how could I get that? I just told you, if I can interpret that coefficient as a 1% change in X causes this percent change in Y. If I think about putting, oh wait, no, price elasticity, so I do want it. Okay. If I think about putting the natural log of quantity, now I can think about 1% changes in price would cause quantity to change by whatever my coefficient is, right? Which is essentially a price elasticity, right? So these log-log models, you can almost think about like how we kind of apply them, some other things that you might have heard in the past. I mean, this is stuff that I'm sure you guys did in 201. I'm sure you hated elasticities, so I probably shouldn't have brought them up, but that is something we could use. Where do these actual numbers come from? It would come from something like a log-log model, right? So we've got our percentage change in quantity, or whatever we're thinking about. So I could run it kind of my regression using my natural logs, and yeah, this is just something maybe that relates to stuff you've seen from other classes. Okay. So with that being said, log-log models are great, but we can also do things like level log, where I'm only looking at the maybe natural log of one of my variables. Right? If I can get this to work. So I could do a log level or a level log, right? The way we want to think about this is this first term refers to my y variable, and the second word refers to my x variable. So if I'm taking a log-log model, that's take the natural log of y and the natural log of x. A log level would be I take the natural log of y, but I leave x alone. I leave x in its units, or the level of x. And then level log would be I leave the y variable alone, but I take the natural log of the x variable. Okay? So if we think about a log level, I've taken the natural log of y, I've left x alone. The way we interpret beta 1 now is if I think about if x goes up by 1 unit, beta 1 is not the percentage change in Ly. It's almost like, it's not a proportion, but we can think about it to turn it into a percentage, we're multiplying it by 100. So a 1 unit change in x would cause the predicted y value to go up by beta 1 times 100, okay? So if I have this log level model, basically the way you can think about it as you think about changes in x, whatever x is. If you didn't take the natural log of x, you're thinking about 1 unit changes in x. If you did take the natural log of x, like up here, right? Now we interpret it as a 1% increase in x, right? So kind of x kind of gives you an idea about what you're thinking about the changes in, okay? So here, 1 unit change in x causes y to go up by beta 1 times 100. kind of think about it as, well, we had kind of use this natural log to convert percentages. So I don't want to know the change in the natural log of y. I want to know just the change in y. So whatever that coefficient is, I have to multiply by 100. The level log model is I leave y alone, but I take the natural log of x. Well, now, because I've taken the natural log of x, the way I interpret beta 1 here is a 1% increase in x causes y to go up or down by beta 1 divided by 100. Okay? So if I'm going from kind of, units to natural log, I have to multiply by 100. If I'm going from the natural log to units, I have to divide by 100. Okay? So those are kind of our different interpretations of these different models. I could basically, once I had that in Excel, those new columns, well, now it's just in my regression tool, select the natural log of y as my y variable and x as my x variable, and now I'll get a log level. If I wanted a level log, select my original y variable, but select that natural log of x as my x variable. So what model, which of these should we use? Well, for the sake of what we're doing, we're going to kind of look at this r squared, right? Using this r squared to start to think about what models better fit this relationship. Right? So we could just run all four and say, well, whichever one has the highest r squared there, that's going to be the most predictive model. So that's the one I'm going to want to use, right? So I'll just run all four, look at the r squared, and then that's going to be the model that kind of most accurately captures the relationship between x and y. Right? So I could kind of run through this in Excel. I'll get a little bit of time, yeah. And we can kind of think about how we would do this. Why does it keep exiting out when there we go. So I've got, where's my height weight data? Where's my Excel files? Okay. Oh, I've got it in another course because I've done it before. Which one of these has height in it? Does this one have height in it? I think this is an ANOVA example. Yeah, I don't want that. Let's try it. Well, let's do it with SAT GPA, and I'll try to find out which one of these has a 0. So if I select this data set, right, and I go up here to data, I'm going to filter it. I'm going to look and see if there's any zeros or blanks here. So that one's okay. Oh, this is my natural log one, so that'd be good. So number. So here's the one that I'm having kind of an issue with. So deselect all. Select this guy here. Sure enough, there were some zeros in that college GPA. Guess these were people that just decided to never show up and not drop, right? So I'm going to delete those for the sake of this example. Hit OK here. Okay. I'm going to do something a little bit. Do a new sheet so we can kind of keep this a little bit clearer. So I'm just going to copy and paste this over there. And I'll actually put this up on Canvas once we're done in class today. So I've got my variables here. So the first thing I'm going to do, data analysis. I'm going to select college GPA as my Y variable and SAT score as my X variable. So I'll put this on a new worksheet and call this level, right? I'm then going to go back and I'm going to basically just run all of my different regressions. So the next one I might want to do, and I'm not going to select it because I can do it a little bit quicker. All I have to do is change the columns I want. So, oops. So here I'm going to look at C. Oh, that's not what I want. There we go. C1 to C, 455. And my X variable, I'm going to use the natural log of the SAT score variable. So I'll change that to column D. So now I'm going to use a log model. Hit enter. That's my log model. Okay. And then I'm going to go through data analysis, regression. Now I'm going to leave, oops, except for I'm on the wrong sheet. So now I'm going to just use the natural log of GPA as kind of my y variable. But my x variable, I'm going to change to just, why does it keep going back there? Oh, because I selected the thing. Now I'm going to change my x variable to be just level, right? Normal SAT. Okay. So I hit OK. Well, it doesn't like this. Let's get rid of these. All right. So the reason why that happened, I'll show you. You should start out on the data sheet that you're on when you go to this data analysis tool, because that's why I was trying to reference all the sheets and I didn't want to. Okay, so now I've got it. It's selecting the natural log of GPA is my y variable. Now my x variable I'll keep as the level of SAT score. So now everything should be okay. Okay. So there I had a log level. Since my y variable is log and I left my x variable alone, we've got one more that we need to run, which is I'm going to leave my GPA as a level, and I'm going to make my x variable the SAT score, use the natural log of it. So now I've got here a level log. Okay. Once I have this done, and this is what I think I have you do on one of the last questions in that Excel assignment, I've got my R squared. So 0.16, 0.12, 0.12, 0.168. So just barely here. Actually, I shouldn't have monkeyed around with this at all, because the relationship between SAT and GPA in terms of, these four models is more accurately captured by the level than any of these other three. Okay? So that's all you have to do when you're thinking about which model best fits the data. Go through, look at the R squared, whichever is higher. That's the one that most accurately captures that relationship. Okay? Any questions on any of this in Excel? Also, I had a couple people email me. Make sure that you at least try to download that data analysis tool into your computer. So if you're having any issues with that, you can let me know ahead of time and we can kind of troubleshoot it. In fact, was it Nolan reached out to me? His issue was just basically restarting it a couple times. So I don't know, sometimes it has a little bit of issues. So make sure you try to get that data analysis thing added in. And if you can't, let me know and we can try to troubleshoot it together. Okay? All right. So if you want to show up on Monday, no matter what group you're in, I'll be here. Have a good weekend. Enjoy the nice weather today, and I will see you on Monday.